Now we move to this last chapter in this textbook. In the printed textbook, Larson has three further chapters online. Who cares, right? So we're just going by what's in the physical book. In the words of some of my favorite cartoons when I was a kid, the Bugs Bunny show with the Road Runner and all those cats, and the announcer would come on and say, "Now for our fast feathered friend, the Road Runner." Here, the eigenvalues and the eigenvectors are the road runners for uh, linear algebra and also differential equations. The cool thing is that in the solution for differential equations, where you have the nth linear differential equation of constant coefficients, that those solutions are actually a combination of the eigenvalues and eigenvectors. Um, so it's pretty neat. But here we focus on applying the eigenvalues and eigenvectors to solving a system of differential equations. So the goal is to solve the system, this differential system. It's not supposed to do that. It's supposed to do that. Now the steps are straightforward. Basically, you're going to take the differential system, look at the matrix A that's contained in it, extract A, and then from there, follow your steps for finding the eigenvalues and eigenvectors from the previous chapter. Now, once you do that, then we're going to claim that the eigenvalues, which would be here this is a 2 by 2, which would be lambda 1 and lambda 2, that they for us forms a pretty neat part of the solution. That is that u sub 1 is equal to c sub 1 times e to the lambda sub 1x, and u sub 2 is equal to c sub 2 times e to the lambda sub 2 x, where u is u sub 1 and u sub 2. Note, I think this textbook may use t for x, where x is equal to t. Then you can write the general solution as y equal to p times u. Recall that P is the matrix that consists of the eigenvectors. If if you're given initial conditions, we can solve them. That is, we can solve for C sub 1 and C sub 2. I think most in this textbook and in Web of Sign, they don't give an initial condition. I will do it here because I know that the application here is so rich that as you go into engineering, you will come across these kinds of systems where you need to solve them using a combination of DE and linear algebra. So for the first problem, we're going to build the matrix A, and this is pretty cool and easy when we just given these monomials. This is negative 3, 0, and this is 0, negative 1/5. So we use what we know in terms of the eigenvalues and eigenvectors, and so we have the determinant of lambda times the identity minus a, and that gives us this determinant of lambda minus a negative 3 is lambda plus 3, 0, 0, and then lambda minus a negative 1/5 is lambda plus 1/5. And again, this is a determinant set to equal to 0, And what that does for us is that yields lambda plus 3 times lambda plus 1/5 minus 0 is equal to 0. So we get lambda equal to negative 3, and then lambda is equal to negative 1/5. So we take lambda to be negative 3. We plug that back into the matrix. It's just the matrix of lambda I minus a. So we plug this into here. Remember the notation. This notation is for a determinant. So here I write just the regular notation for a matrix. So we plug in lambda to equal negative 3. We get 0 there, 0, 0. And then we get negative 3 plus 1/5. So we simplify. This is 0, 0, 0. This is negative 15 plus 1, negative 14 over 5. Now we reduce this, basically reduce row echelon. So we divide row 2 by, or multiply row 2 by a negative 5 over 14. So we get 0, 0, 0, and 1. Now, since the idea of the eigenvalue is to actually break the system to be able to try to find something neat from it. So here the idea of the characteristic equation is that you force a matrix to have infinitely many solutions. Pretty cool, right? The Germans came up with it. So from here we basically find the null space, and notice here that that x of 1 would be is infinite, because for the first row we get 0 and 0. So let x of 1 equal to t, but x of 2 is times 1 here. 1 times x of 2, that's equal to 0. So the eigenvector that we get is consists of 1 and 0. Okay. Now let lambda equal to that negative 1/5, and so this implies that we look at lambda times I minus a, and you can replace the lambda with negative 1/5, by the way. So here we get, I look at this guy, and so negative 1/5 plus 3, 0, 0, and then this is 0. So we reduce that, we get negative 14 over 5, 0, 0, 0. Then you can reduce that to 1, 0, 0, 0. Now that implies that the eigenvector for this one, notice that we'll let x of 2 equal to t, x of 1 is equal to 0. So this gives us 0, 1. So the matrix P is what we're after. The matrix P consists of the two eigenvectors, this one and this one. And so that's 1, 0, 0, 1. Just the identity. and no need to solve this system, and I probably just could have told you that if we're given these values for A, and it's a diagonal matrix, then the terms along the main diagonal become automatically the eigenvalues, and automatically the matrix P will be the identity matrix. Pretty cool. So now our solution is said to be y is equal to P times U. And so P is this identity matrix times U. What is U? We need to fix that up. U consists of, I need to write that out. I thought I did. Sorry. So U sub 1 is equal to C sub 1 times e to lambda sub 1 times x or t, whichever variables they're using. I think they're using t here for this textbook. So that first lambda is -3, let's say times t. And then we'll put U sub 2 is C sub 2 times e to the -1/5 t. So the solution y is equal to P times U. P is the identity matrix, then times here U, C sub 1 times e to the -3t, and C sub 2 times e to the negative, let's just say t over 5. And this implies that within y is y sub 1 and y sub 2. So since I have it like this, we'll just keep it as a matrix. So y sub 1 would be 1 times the C sub 1 times e to the -3t, and then plus 0 times C sub 2, but that goes out. And then for the second position, we get 0 times C sub 1, that goes out, plus 1 times that C sub 2 times e to the negative t over 5. And those are the solutions there. Well, let's keep digging. So here we need to write this. We extract the matrix A. So this is 1, 5, 5, and 1. And so now from here we want to solve for the eigenvalues. So we look at the determinant of lambda times I minus A, and that gives us the determinant of lambda minus 1, -5, -5, lambda minus 1. So we solve that, and that gives us lambda minus 1 to be squared minus 25. And that's equal to lambda squared minus 2 lambda plus 1 minus 25 is equal to 0, because we set this characteristic equation equal to 0. And so this implies that we have lambda squared minus 2 lambda minus 24 is equal to 0. Well, that gives us lambda minus 6 times lambda plus 4 is equal to 0. So this implies that lambda is equal to 6 and lambda is equal to -4. So now we solve for the eigen vectors. So let lambda equal to 6, and we plug that into the form. We're plugging that into lambda I minus A, just the matrix, not the determinant. So we plug that in, see if I can write it here. Sorry about that. So we plug in the lambda to be 6. It gives us 5, -5, -5, and a 5. Now reduce that. So in row reduction, this becomes a 1, -1, 0, 0. That implies that x sub 2 is equal to t, and x sub 1 is x sub 1 minus x sub 2, or x sub 1 minus t is equal to 0, so x sub 1 is equal to t. So the eigenvector becomes 1 and 1. Now let lambda equal to the -4. So that implies that this system here, plug in the lambda to be -4. So that gives us -5, -5, -5, and -5. And so we reduce that. That gives us 1, 1, 0, 0. So notice that x sub 2 is the floating parameter, and x sub 1 is equal to -t. So this implies that p sub 2 is equal to -t in t, or that is, it's times a t on the outside. We just take the numbers. So the matrix P that we want is 1, 1, and then -1 and 1. And so U sub 1 is C sub 1 times e to the, that first eigenvalue is 6 times e to the 6t, and then U sub 2 is C sub 2 times e to the -4t. So then we multiply the matrix P times U, and make sure I have that somewhere, so when I turn the page I don't have to keep jumping back, right? So let's pick up another page here. And so again, we have U sub 1 is C sub 1 times e to the 6t, and then U sub 2 is C sub 2 times e to the -4t, and then that matrix P we got to be 1, 1, -1, and 1. So Y is equal to P times U. And so we get 1, 1, -1, 1 times U, which is C sub 1 times e to the 6t, C sub 2 times e to the -4t. And that gives us, just do the multiplication, so we get C sub 1. Guess we can say it like this, that this Y is, the Y sub 1 is the first one. So that's C sub 1 times e to the 6t minus C sub 2 times e to the -4t. And then this is being applied over here, so Y sub 2 is equal to multiply this row times this column. So that's c sub 1 times e to the 6t, and that's plus c sub 2 times e to the negative 4t. Now, in terms of what's presented in this section, that's basically it. Let me give you a problem that I used to cover back in the old world, where they gave us initial conditions. So same problem argument, but they give us these initial conditions. So we got to go one step further. So yeah, that's not supposed to happen. So we have a is equal to 1, 2, 4, and 3. And so then we find the determinant of lambda times the identity minus a, and that gives us lambda minus 1, negative 4, negative 2, lambda minus 3. And then solving that, we have lambda minus 1 times lambda minus 3 minus 8 is equal to 0. So it gives us lambda squared minus 4 lambda plus 3 minus 8 is equal to 0. So we get lambda squared minus 4 lambda minus 5, and that's lambda minus 5 times lambda plus 1 is equal to 0. So then we take, remember that lambda times the identity minus a, not the determinant. See the difference in the notation? This is lambda minus 1, negative 4, negative 2, lambda minus 3. So let lambda, we get two lambdas. Lambda is equal to 5, and then lambda is equal to negative 1. So take lambda to equal to 5. And when we do, we plug that in to this guy. And so it gives us 1, negative 4, negative 2, and then 5 minus 1 is 4, and then 5 minus 3 is 2. Reduce this. So in reduction, I interchange rows 1 and 2, and then I canceled out the second row, and then I divided the first row by a 2, say negative 2, so I end up with 1, negative 1, 0, 0. On your calculator as well, you get the same thing. So in doing that, the eigenvector, you see, let have a 0 here, so that's what you let to be the floating parameter. Let x sub 2 equal to t, and that first equation is x sub 1 minus t equal to 0. So this implies that p sub 1 is t, and t, or just say 1 times 1, then times that t. That's fine. Secondly, let lambda equal to the negative 1. That's the other eigen value. So the matrix that we get, we plug in lambda to equal negative 1. So we get negative 2, negative 4, negative 2, and negative 4. Now I can cancel out the second row from the first row, and then after that divide the first row by a negative 2. It leaves me with a 1, a 2, a 0, a 0. So do you see that the eigenvector would be negative 2 and 1? All right, do you see that? So let x sub 2 equal to t, then the first row is x sub 1 plus 2t is equal to 0. So we get x sub 1 is equal to negative 2t. So p sub 2 is equal to negative 2, 1 times t. So then we take p to be 1, 1, and then negative 2 and 1. And then, we get u sub 1 is c sub 1 times e to the 5t. And then u sub 2 is c sub 2 times e to the negative t. So then we put them together, and see, let's add a so solve y equal to p times u, and so p, we got that to be 1, 1, negative 2, 1. And then times u, c sub 1 times e to the 5t, c sub 2 times e to the negative t. So that implies that y sub 1 is equal to, just do the multiplications, c sub 1 times e to the 5t minus 2 times c sub 2 times e to the negative t. And then y sub 2 is c sub 1 times e to the 5t plus c sub 2 times e to the negative t. Now they give us some initial conditions. They tell us that y sub 1 of 0 is equal to 2, and then y sub 2 of 0 is equal to 1. Right? So solve by the initial conditions. So y sub 1 of 0, just replace the t with 0, so that we end up with c sub 1 minus 2, c sub 2 is equal to 2. And then y sub 2 of 0 is equal to c sub 1 plus c sub 2, and that's equal to 1. Make sure I got those numbers right. That is 2 and 1. Yep, good. So now we just solve this system. Solve it any way you want. Just put it back into a matrix: 1, 1, negative 2, 1, 2, and 1, and then just reduce that. So this is 1, negative 2, and 2. Get rid of that 0. So by multiplying the first row by a negative 1 and then adding that to row 2, so this becomes a 3. This is negative 2 plus 1, that's a negative 1. And then we keep on working with that to simplify. I didn't see that before. Add row 2 to row 1. That gives us 1. Well, I need that to cancel out. Let's do this. Divide row 2 by a 3. And then get rid of this 2 by saying 2 times row 2 plus row 1. So this is 1 and 0. This is 0, 1. We get negative 1/3. So here, to do that, we said 2 times row 2 plus row 1, so that's negative 2/3 plus 2, so this gives us 2/3. And then we erase this to make it seem like we did all the math in our head, right? So C sub 1 is 2/3, C sub 2 is negative 1/3. So you get y sub 1 is equal to 2/3 times e to the 5t, and then that's minus 1/3 times e to the negative t, and then y sub 2 is, c sub 1, this is 2/3 times e to the 5t, and then this is minus, because c sub 2 is negative, minus 1/3. I'm sorry, I'm off. Let me correct it. This last row is right, times e to the negative t. I need to go by this pattern here. I did that for that one by accident. So this has to be negative 2 times c sub 2. So negative 2 times c sub 2, well, c sub 2 is negative 1/3, so that becomes plus 2/3. Okay. And then this becomes the solution. Now, I didn't see a problem like that. Maybe I didn't look far enough, in web assign to give to you in terms of being able to solve for the initial condition. The cool thing is that, guaranteed in engineering and also in differential equations, when you're given that, it's the same thing. You do the same exact thing. Just keep these notes and just do that. Just refer back to them, and you're not learning anything new. If it's a 3 by 3, you just expand it, do the same thing. Okay, so that should do it, and hopefully that helps. Thank you.